All right. So as usual, we have a lot to do today. Like what you say, well, we're going to look at chapter 12 and wrap it up. It's almost done. And then we're going to look at a video, which we've been saving. And then we will start the chapter 12 problem set. And let's see, hold on. Let me go get Moodle. Most likely what's going to happen is we will probably end up doing the sample final on Monday. And if that happens, then that means the following Thursday, a week from today, we would not need to have a class. In other words, that technically is our last class, or would have been our last class in person if we were doing this the normal way in the classroom. Our final exam was supposed to be during the week of the 13th. I don't know if it was meant to be Thursday or Monday. That depends on the schedule. But since we're doing this online, we don't have to worry about that. What I can do is as soon as we're done with the sample final, or even actually, even today, really, I could post it if you're interested in getting started early. So, but the only thing that remains to be determined is what day would the exam be due. So the week, today's the 2nd, of course. So my guess is that we'll be completely done with everything on Monday the 6th. So that means we can have a day off on the 9th. And the week of the 13th was the final exam week, or it still is. So sometime during this week is when the due date would be. Now, let's go back to Moodle for a second. I just want to see if I hadn't already put up an announcement about this. I don't remember if I did or it doesn't. Oh, okay. So I've got a chapter 12 problem set. Yes. Oh, okay. So good. I did mention that we want to do the chapter 12 problem set on Thursday. The following week, we can work on the sample final. So, let me just see if I can identify or figure out when we were supposed to have our exam. Because that'll help determine how much time I can give you to do the final exam. All right, let's take a quick peek at this. So we are, of course, Monday and Thursday. 10:30. There we go. So according to this, we were supposed to have our final exam on Thursday, the 16th. Okay, so if that's the case, they normally give me a few days to correct it and hand in the grades. So although I'm sure you will not need anything like that much time, why don't we agree that you can have it ready as late as that Sunday, although I do not encourage you to wait that long. Since we were going to do it in class on Thursday, the 16th, let's see, let me just check something. No, all right, so we're going to have it on the 16th. What I really need to see is when the grades are actually due. Not that I want you to wait to the last second, but this gives me an idea of how much time you can actually have. So it should say here somewhere, when is the absolute last day to hand in the grades? And by the way, I'm going to grade them as you send them in. And so in other words, once you send me your final exam, I can actually just post your final grade. So the sooner you want your final grade, the sooner you can send it in. But it looks like the following Wednesday. Oh, that's fine. All right. So here's let's do this. Let's just say that they should all be ready by, wow, that means you have until Sunday the 19th. Ooh, that's a long time. But like I said, I would strongly encourage you not to wait that long. But if you're desperate for time or something's going on, it's fine. So let me make an announcement. So that means that the last day on which you can submit your final exam will be Sunday, December 19th at midnight. I encourage you to send it in as soon as possible. But if you need the time, you can have until Sunday the 19th. All right, so, try not to wait that long unless you're really desperate. You've got so much other stuff going on that it can't be done sooner than that. All right, so let's just agree to that. And remember, the final exam is only in the last 2 chapters. So, all right, I think that's enough. So that's where we're heading today and Monday. And so that's that. So let's get back to what we were doing. We'd actually started chapter 12. In fact, actually, we got a long way through 12. We only have one more topic to cover. Although it's a very complicated one, it's also quite important. So let's get that back open. Now, I do have one final video for you, which is based on what we're doing right now. Let's see, where is it? There it is. Correlation does not equal causation. This is more of a big picture look at what we're about to do. It's more conceptual than computational. They're going to try to explain to you what we're doing and what it actually means. So we'll save that, of course, until we're actually done with the notes. All right, here we are. Let's get this open. There we go. All right, so we're going to finish this up. Now, when you see this section, the formulas will look very, very frightening. But on the exam, if you look at the, oh, by the way, let me go back to Moodle, make sure I posted everything. There it is. Oh, good. Okay, so you've got your chapter 12 problem set right here. The sample final is here. So if you look at the sample final, let's get that open. Yeah, it looks like the sample final does not actually have any questions about the topic that we're about to look at. So really, this is more for your own benefit. So like I said, if it looks terribly scary and all, it kind of is, but it's important, but it's not going to actually appear on the final exam. Okay, so in other words, the sample final is telling you what you can expect on the actual final. So because it's such a complicated topic, I've chosen to leave it off of the final exam. So you can kind of relax a little bit while you're watching this. And like I said, the formulas look terrifying, but the concepts are very important. And it's important that we understand what they're all about. So, but you won't be asked to do that on here. Okay, so in others, from experience that the actual exam will be very similar to this. So there aren't any questions here about the last 2 measures we're about to look at, which are correlation and covariance. Okay, well, that's nice. Now, what about the the chapter 12 problem set? Let me see if I put one in there. No, it's not there either. All right, that's good. All right, that's what I thought. All right, so I'm going to show you this topic, but keep in mind, you're not actually going to be asked to do this on the final exam. So it's really more for your own benefit. Right? So anyway, what is all this discussion? What is it that's so scary that I'm so reluctant to put it on the final exam? All right, well, let's find out. So way back in the beginning, we mentioned that there's 3 types of measures that we might be interested in studying in statistics. All right, let's go back and revisit that. We have measures of, okay, measures of central tendency, measures of dispersion, and measures of association. We've already looked at these first 2. Remember, the measures of central tendency were the mean, median, and mode, and they help us find the center of the data. The measures of dispersion were the range, the variance, and the standard deviation, and they help us determine how spread out the data are. Then finally, we have the measures of association, which is a different type of measure because it looks at 2 different samples or 2 different populations, and it tries to determine if they follow each other very closely or not. In other words, we're trying to attempt to determine if they're related to each other in any meaningful way. Like, for example, you might discover that, let's say there might be a strong connection between the price of gas in New England and the price of gas in New York State. It may be that they're very closely related to each other, or it may turn out that they're not really related at all. We don't know until we look at this measure. Oh, I almost forgot. One of the measures of dispersion was the coefficient of variation. Okay, so there are 4 of these, which we saw last time. But now we're finally ready for this scary new type of measure, the measures of association. All right, so let's see, what is this all about? So a measure of association shows the degree to which 2 variables tend to move in the same direction. And the 2 most important ones, as you can see there, are the covariance and the correlation. Now you can see in here is the word variance. The variance refers to a single sample or population. Covariance indicates that this refers to the variance of 2 samples or 2 populations. Correlation is something you may have heard this word before in everyday life. You do run into it from time to time. Especially if you're watching certain shows like crime dramas, Law and Order, and any shows that involve a lot of scientific analysis of crime scenes, they often throw these words around because what they're trying to capture is whether there tends to be a connection between 2 different variables. Like, is there a stronger tendency for people who live in the city to buy certain products than others, or to spend on certain items more than others? So this is something you bump into in the real world quite often. Now, we have a special type of graph that is designed to help us understand the relationship between 2 variables, and it's called a scatter plot. Okay, whoops. And so the scatter plot can be easily implemented in Excel. So let's see. I may already have some examples already set up here. Here we go. Yeah, in fact, now that I think about it, I think we've already started discussing this, didn't we? I forgot all about this. Yes. Remember the other day we put these together. In the first case, we have sales and profits. And it's pretty clear that there must be a direct relationship there, or positive relationship. Obviously, the more merchandise a company sells, the more profits they'll have, or typically that's how it works. So here the points are moving in, you can imagine these moving in a northeasterly direction. And so, but the important detail is this line, which is called a trend line, has a positive slope. It means that as you move to the right, as the sales are increasing, there's also a strong tendency for their profits to increase. So these 2 variables are positively related to each other. And the measures we were just looking at would enable us to determine not only the direction of this relationship, but how strong it is. All right. Now, let's say in the next slide sheet, we had the opposite. We had profits and the cost of raw materials. Now, obviously, if it costs more money to produce your product, you're going to have lower profits. So it would be like, imagine if Starbucks suddenly found that the price of coffee beans suddenly increased dramatically. You can imagine that that's going to have a major impact on their profits. They'll have to pay more for their coffee beans. They can't realistically jack up their prices very much because they could lose business to their competitors. So most likely they would end up losing money, or at least their profits would be reduced if the cost of coffee beans suddenly went up. And this does happen sometimes. Certain parts of the world where coffee grows well, sometimes they might get hit by hurricanes or something else can go wrong. And before you know it, coffee bean prices are going through the roof. The same thing happened a couple of years ago with the vanilla crop in Africa, where most of the world's vanilla comes from. There was terrible weather for like a few years in a row. And all of a sudden, vanilla became horribly expensive. And so the producers of vanilla would have found their profits being reduced as a result. All right, anyway, then there's a third possibility, which we see in many applications. It could just very well be that these two variables have nothing to do with each other, like profits and temperature. Unless this company makes, skiing equipment or something, it's not likely that the temperature will affect their profits. So we end up with this random scattering of these dots, and the trend line is flat, or in other words, it has a slope of 0. Okay. Now, what we're trying to do here is actually capture or assign a number that explains what we're seeing here. Okay, that's what these measures are all about. So we'll start with the covariance. Oh, one more thing, I have to save this again. Wow, it's already December. It's hard to believe, isn't it? Yes. Okay, so covariance is a measure that can either be positive or negative or 0. If the covariance is negative, then you have this case. All right. The fact that the covariance is negative simply indicates that the direction of this relationship is negative. In other words, when one goes up, the other goes down, and vice versa. If the covariance is 0, the next and y are said to be unrelated to each other or independent, and that is this case. All right. Now, it doesn't have to be precisely 0. As long as it's close, that's good enough. To conclude, I mean that the variables are unrelated to each other. And then, oh, did I miss one? Oh, it's way at the top. I overlooked it. When the covariance is positive, that would be this case. And it simply means that they're going in the same direction. Now, what the unfortunate thing about this, though, is that it's hard to tell how strong this relationship is. So in other words, what am I referring to here? Let me just show you a couple of cases where the covariance is positive, and you'll see that they can be very different. Let's see, where could I put this? So the covariance is an attempt to measure both the direction of the relationship between two variables. In other words, positive, negative, or 0, as well as the strength of the relationship. So let me show you what I mean by that. Let's say that there's two cases where we have a positive covariance, and we're going to see that there are two very different scenarios. In the first case, we have two variables that are closely related to each other, really close. So here's the trend line, and the points are extremely close to that trend line. They're almost all sitting right on top of it. So we'll call this a close or strong positive relationship. On this side, though, look at this one. So, well, I mean, you can see the points are heading up in the same direction, but they're not very close to that line, are they? This is what we would call a weak positive relationship. So you can have you can have positive relationships that vary in strength from very strong to very weak. And so the covariance measure helps us identify which is which. So this one will have a very high covariance. Or I should say a high positive covariance. And this one will have a very low, but still positive covariance. Okay, so now this can work in the negative direction too. And again, let me show you a couple of graphs that illustrate this. How about these two? This would, of course, be a strong negative relationship. And then here's one. It's not very strong, is it? It is negative, but it's a weak negative relationship. All right, so here you would have a high negative covariance. And here you'd have a very low negative covariance. And again, because you can see we're trying to capture not just the direction of the relationship, positive or negative, but how strong is it. Okay. Now, there's another possibility. Let me just remind you that what about the case where they're not really related at all? And so you get something like this, a flat trend line. And these are two variables that are simply unrelated to each other. So the covariance will be very close to zero. The variables are unrelated. Or sometimes we say that they're independent. Like the case we saw with the corporation's profits and the temperature. All right, so the point of calculating this measure is to get a sense of how strong this connection is between the variables. All right, so now like with some of the other cases we've seen, there's going to be a sample covariance and a population covariance. And you can tell this is a sample version because it doesn't involve Greek letters. SXY will from now on be used to represent the sample covariance. It has two subscripts to remind us that this is the covariance, not the sample standard deviation. We have two samples, X and Y. The mean of the X's is, of course, X bar. The mean of the Y's is Y bar. So look at this formula. Oh my God. We have to go through all the X's, subtract their mean, do the same thing with the Y's, and then multiply them together. In the denominator, we have the common sample size of the two samples minus 1. All right, so let's look at some actual data. Now, the first thing we need to do is calculate the means of the two samples. And of course, as I think I mentioned, the two have to have the same number of elements. And here they are. So let's see. What would be X bar? You would add these up, as you know. And it's that simple. Now, y bar, so the numerator there, we have 15/5 or 3. Okay, so x bar is 1, y bar is 3. Okay, now that means, now watch what we're going to have to do. Now, this is a lot of work. I'm going to tell you right now. In fact, you know what? I wonder if I can, let me try something here. I'd like to have the data visible to you. Let me try and see if I can squeeze this on here so you can follow it more easily. Ooh, it's a bit of a mess, but I think we did it. All right, so those are the actual elements in our samples. So what this catastrophe is saying to me is that this is x1 minus x bar. This is y1 minus y bar. Here we have x2 minus x bar and y2 minus y bar. And then we go on and on and on. So in fact, let me see if I can squeeze in some more room here. So you can see this must be x3 minus x bar, y3 minus y bar. Then we have x4 minus x bar, y4 minus y bar. And finally, at the end, let's see. There we go. I made it fit. X5 minus x bar, y5 minus y bar. And again, you notice we're dividing by n minus 1. And when you do the numbers, you plug in, you calculate what you've done. And we have -1 as our covariance. So that means that there's a connection between these two, which is negative. Now, it's not a terribly strong connection, although here's one of the real issues with the covariance. -1, it's hard to tell if that's a large or a small covariance. This is one of the real weaknesses of the covariance measure. We don't know, without graphing this, if that's a strong or weak connection. We know that it's negative, but it's hard to tell how strong it is. In fact, you know what we could probably do here? Why don't I put the data in here and let's take a look. All right, so what do we have here? 1, -2, 303. Then we'll have 3, 2, 4, 6, 0. All right, so what I'm going to do is ask Excel to plot this for me. It certainly has the capability of doing scatter plots, as we know. Now, with so few points, it's not going to look like much, I can tell you, but we can get the gist of it. So I'm going to ask it for a trend line. You can see it's negative, but that's not a very strong connection. The points are really, except for this one, the points are really not particularly close to that line. So it appears that the covariance of -1 is a very weak relationship. It's negative, but it's very weak. But the problem is it's hard to say when you're just looking at that -1. And so that's one of the really big weaknesses of the covariance measure. So what can we do about it? Is there another approach we can take that will give us a number that not only has the right sign, but gives us a better feel for how strong this relationship is? And that's when we introduce the correlation coefficient. Now, before we do that, I just want to show you, this is the equivalent formula for the population covariance. And you can see we changed all the Roman letters to Greek letters. These replace the X bar and the Y bar. This replaces SXY. And of course, we have the capital N's, but other than that, oh, and one more thing. Like with the variance, here we're dividing by N instead of N minus 1, like we did here. So that it has that in common with the variance. All right, but having said that, let's jump ahead and look at the correlation. Correlation is closely related to covariance, but here's the beauty of it. The range of possible values is from -1 to +1. It can't fall outside that range. So when you see a correlation number, it's easy to tell not only what direction the variables are moving in, but how strong is that relationship. All right, so let me just show you a couple of quick examples. If I had a very strong positive relationship, what will happen is the correlation coefficient will be close to the maximum value of 1. Let's say that the correlation in this case is 0.9. And that reminds us that it's not only a positive relationship, but a very strong positive relationship. Now here, man, this is a very weak positive relationship. Let's say in this case, the correlation is 0.1. So here we have a very strong positive relationship. And here we have a weak positive relationship. But now, see, unlike before with the covariance, I couldn't tell just by looking at that number. Now I can. We know that the correlation is always between negative and +1. It cannot fall outside that range. So anything close to 1 means it's a very strong positive relationship. Anything that's closer to 0, like this 0.1, means it's a weak positive relationship. All right, now what about the opposite cases, the negative cases? Well, it'll be very similar. A very strong negative relationship. Let's say in this case, the correlation is -0.8. Not perfect, but very close. This is a strong negative relationship. And then we might have something like this. Very negative, but very, very weak. All right, you get the idea. And so in this case, let's say that the correlation is -0.1. Weak, but negative relationship. Okay, so we can tell both just by looking at the number. It's not only negative, but it's either strong or weak. And that's the nice thing about this measure, which we did not have with the covariance. All right, and then what about the case where the relationship essentially does not exist? In other words, two independent variables, you'll end up with a scattering of points, a flat trend line, and here the correlation is just 0. All right, now I want to show you two more special cases though. All right, just so you can see what they look like. So this is the zero case. They're just not related to each other in any meaningful way. All right, now how about this situation? Oh, that's nice. They're all on the line. Here, the correlation is exactly 1. Here we say that the variables are perfectly positively correlated. That's one extreme case. And then the other extreme possibility is this one, as you can probably guess. The correlation is at the other extreme, -1. And we say that these variables are perfectly negatively correlated. So you don't see that very often in the real world, but this is the theoretical limit to how high and how low correlation can go. Now, how do we derive the correlation from the covariance? Okay, let's see what this looks like for the sample correlation first. And you'll see that it's just a function of other things we've already seen. Oh, look at this. So by the way, this R is often called the correlation coefficient. And since it's based on a sample, it's specifically the sample correlation coefficient. This is the sample covariance. This is the standard deviation of sample X. And this is the standard deviation of sample Y. So you can see it's a bit of a mess. And you're now thinking, oh, I'm very happy now that I won't have to do this on the final exam. No, but I want you to understand how this works, all right? So the calculations are very time consuming, but it's an important idea. Now, what we're going to do now, remember that last example where the covariance was -1 and we couldn't be sure if that was a strong or a weak connection. So we're going to take that same sample data we had from way back here. And now we're going to calculate the standard deviations for X and Y and plug them into this formula. Okay, so remember, we found that the sample covariance was -1, but we couldn't be sure if that was a strong or weak relationship. Although, based on our Excel spreadsheet, we suspect that this is a very weak relationship. We're going to prove it by calculating the correlation. All right, so I went ahead and did both sample standard deviations. For X, the sample standard deviation is approximately 2.1213. You don't have to do this right now. You know how to do this. And for Y, it's approximately 2.2361. Okay. So when you bring them all together, look at that. It's just as we thought. It's a very weak negative correlation. The relationship is weak, but negative. And again, now it's easy to tell by looking at that -0.21 as opposed to this -1. The -0.21, the correlation coefficient, makes it easy to tell that this is not only a negative relationship, but a very weak one. And that's why the correlation is typically preferred to the covariance measure. And then you'll hear, like I said, in practice, you'll hear the word correlation thrown around all over the place. And this is what they're referring to. Like, for example, if we discover that there's a strong correlation between advertising expenditures and profits, that would tend to indicate that advertising is successful for a corporation. We can't be sure that people are actually buying the product because they saw it on TV, but it's suggestive that they probably are, because if every time we raise our advertising budget, our sales tend to go up, that would be a good sign. And that's one way in which we could use something like this. All right, and then there's just one last thing to consider. That would be the equivalent version for a population. So as you can probably guess, we're going to replace these Roman letters with Greek letters. In fact, let me copy this so you can see them side by side. And you'll see that really, the only thing that's changed here is that we've introduced one more Greek letter, which we haven't seen before. And that would be this. This is the Greek letter rho. And whenever you see that, you're looking at a correlation coefficient for a population. All right, so that's the end of that. Now, the next step is to watch that video that I promised you, because it's going to explain to you a lot of important details about correlation. It turns out in the real world, it is easy to be deceived by the correlation coefficient and draw incorrect conclusions about a population of data. Specifically, what they're going to address is this question. Suppose I told you that there's a very strong correlation between two variables. The question is whether that implies whether one variable actually causes the other to have a certain value. Like I was saying with advertising, what if we were told that there's a strong correlation between advertising and sales? Does that prove that the advertising causes people to buy more products? Well, not necessarily. There could be a lot of other things going on as well. So we have to be very cautious about the way we interpret correlations. Okay, so that's what this is about. And you're going to see that it's possible, easy to lead yourself into some very strange results if you're not careful about the way you think about correlation. So let's get that video going. And you'll see what that's all about. And I think you'll find it very interesting. All right, where is this? There it is. Correlation does not equal causation. All right, that's what this is all about. So hold on 1 second. I'll send you the link. And I think you'll find this very interesting. All right, here we go.
Grammarly Business offers AI-powered writing assistance for your enterprise.
Hi, I'm Adrienne Hill, and welcome back to Crash Course Statistics. Today, we're talking about relationships. No, not why your cat just doesn't seem to like you. We're talking about data relationships, like how you can use one variable to predict another. Like if you can predict whether or not people who write in all capital letters are more likely to default on loans, whether people drive faster after they watch Fast and Furious movies, or whether people blink more often when they're lying. We'll start with this simplest data relationship, one between two continuous variables, also called bivariate data. But first, we're going to need to visualize our data using a scatter plot. The scatter plot has been called the most versatile, polymorphic, and generally useful invention in the history of statistical graphics. Impressive. And as such, they're pretty much everywhere, including on your favorite news site. News outlets now have data journalists on staff to visualize and make sense of data. To make a scatter plot of old faithful eruption duration and latency, which is the time between eruptions, we put one variable on the x-axis and the other on the y-axis. Then each data point is placed so that it's in line with both its eruption duration and its latency. Now we can start to see a relationship. There are clusters, two blobby-looking groups of points, which supports our guess. There are likely two kinds of eruptions, one with a longer buildup and a longer duration, and one with a shorter buildup and shorter duration. Just like the histogram and dot plot, a scatter plot allows us to see the shape and spread of data, but now in two dimensions. This data is clustered, but scatter plots are useful for identifying all kinds of relationships, both linear and nonlinear. For now, let's focus on linear relationships with a classic example, the relationship between the heights of fathers and sons. It makes sense that a tall father would produce a tall son, but we can do better than just a hand-wavy statement. In 1903, the statistician Carl Pearson published an influential paper in his own journal, Biometrica. One section of the paper describes the relationship between the heights of dads and their male children. In this paper, Pearson fit a line through the data to describe the relationship rather than just relying on his eyes to see a pattern. The line, called a regression line, is the line as close as possible to all the points at the same time. And note here, Pearson used feet and inches in his paper, so we will too. Lines are a great way to describe a relationship because they have a nice formula, y equals mx plus b, just like you learned in algebra. The m, or slope, tells you a lot about your data. It tells you that an increase of 1 inch of a father's height leads to an increase of m in the son's height, about ½ an inch in Pearson's paper. So on average, dads who are 6'1" have sons that are about ½ an inch taller than the sons of fathers who are 6 feet tall. That allowed Pearson to make a prediction about the height of the son from the height of the father. And this is why these lines are so useful. They allow us to pretty accurately predict one variable based on the value of another. The relationship between car weight and gas efficiency allows us to be pretty sure a smart car gets better mileage than a Hummer. One note of caution here. The slope relies heavily on the units of x and y, since it's a measure of how many units y increases with each increase of 1 unit in x. If I decided to measure the sun's height in meters, the m, or slope, will change, even though the relationship didn't. When we see a non-zero slope, also called a regression coefficient, it's a sign that there's some kind of relationship between our two variables. But that's pretty much all it tells us. We don't know how strong that relationship is. For more information, we need to look at correlation. Correlation measures the way two variables move together, both the direction and closeness of their movement. You may have read articles that claim there's a positive correlation between exercise and heart health. That just means if you exercise more, your heart tends to be healthier. A positive correlation looks something like this on a scatter plot, while a negative one, like the correlation between the number of cigarettes smoked each day and lung health, might look like this. Higher values of cigarettes smoked tend to have lower values for lung health. We now know what correlations look like in general, but to understand them more deeply, we're going to take a closer look. If two variables have a positive correlation, they move in the same direction. We can see this in our scatter plot if we draw 2 lines across the graph, one at the mean of each of our variables, to divide the plot into 4 quadrants. When 2 values are positively correlated, like how many miles you run and the number of calories you burn, most of the points will be in the upper right and lower left quadrants. In these quadrants, the values for miles and calories burned are either both large or both small. The more miles you run, the more calories you burn. The opposite happens when the correlation is negative, like the relationship between vaccination rates and rates of preventable illnesses. Instead of moving together, the variables move in the opposite direction. So the points are mostly in the upper left and lower right quadrants, where either vaccination rate is small and rate of illness is large, or vice versa. Since vaccination rate and rate of preventable illness have a negative correlation, as vaccination rates increase, rates of preventable illness decrease. The more closely 2 variables move together, the stronger the relationship will be, positive or negative. If the points are in all of the quadrants pretty evenly, you just have a blob or a cloud. You don't have a strong relationship. As I mentioned before, the units of your variables can affect the regression coefficient and can also affect the calculation of our correlation. To get around that, we use the standard deviations to scale our correlation so that it's always between -1 and 1. This is our correlation coefficient, R. Interpreting R involves 2 things: the sign of the number, that is whether it's positive or negative, and how big the number is. The sign will tell you whether your 2 variables move together, positive R, or in opposite directions, negative R. A correlation of 1 or -1 would be a perfectly straight line, meaning you can exactly predict one value from the other. Say we looked at correlation of the number of hours you're asleep versus awake. If I know one of those values, I can tell you exactly what the other one is. We all only have 24 hours in a day. Even Beyonce. As you get closer and closer to a correlation of 0, the points are more and more spread out around our regression line. And eventually, at 0, there's no linear relationship at all. It's just dots. When you look at a scatter plot, remember that you can't deduce a correlation just by the steepness of the regression line. In our earlier father-son heights example, we changed our units to meters and our line didn't look as steep, even though it's the same data. Data with steep lines can have low or high correlations. We also use the squared correlation coefficient, R squared. R squared is always between 0 and 1 and tells us in decimal form how much of the variance in one variable is predicted by the other. In other words, it tells us how well we can predict one variable if we know the other. While they won't usually give R squared an explicit mention, you'll see articles claim things like the ounces of soda a person drinks is highly predictive of weight, which means there's a large R squared. You can think of R squared as a measure of how accurate your guesses would be if you used your linear equation to predict one variable from another. If you had an R squared of 0.7 for the cigarettes and lung health data, that would mean that cigarette usage predicts 70% to the variation in how healthy our lungs are. You could pretty accurately predict someone's lung health if you knew how many cigarettes they smoked. An R squared of 1 means you can perfectly predict one variable from the other, since 100% of this variation is in one variable. This can seem pretty obvious when you think about conversion, like temperature in Fahrenheit can be predicted by temperature in Celsius. In this case, we're not actually measuring the temperature in Fahrenheit, but it's being predicted by Celsius. The higher the R squared, the better the fit. Breaking news from City Hall today. The mayor has announced a plan to cut down on the number of people who drown every year. Sources close to the mayor tell us he's seen some very interesting correlations between drownings and air conditioning usage and drownings and Nicolas Cage movies, or as I like to call it, air cons and con airs. Both are highly correlated with drownings. Here's evidence. If we look at AC sales data over the past 10 years, and even more proof, if we look at Nicolas Cage movies over the same time period, the Nick Cage data was provided to us by Tyler Vegan. So as of today, our mayor has enacted the Cool Cage Act, which will prohibit the sale of air conditioners and create a Nicolas Cage task force that will do everything to prevent Nicolas Cage from starring in any movies. The mayor assures us that because of the strong correlation she saw, as well as the strong will of our city, we will surely have next to no drownings this coming year. The Cool Cage Act may seem silly, but we're constantly flooded with messages that equate correlation and causation. And as you've heard before, correlation doesn't equal causation. Just because two variables are related doesn't mean that one variable causes the other. The examples the mayor uses are perfect examples of things that can go wrong when interpreting correlations. When one thing, A, is correlated with another, B, there are a few possible reasons. A causes B, B causes A. There is a third variable, C, that causes both A and B, even though A and B aren't related, or there's no relationship at all. It's just coincidence. The correlation the mayor saw between air conditioning and drownings is probably caused by a third unmentioned variable, heat. When it's hot, people go buy more air conditioners and they go for a swim, leading to a correlation, even though there's no direct link between the two. And as for Nicolas Cage, he probably shouldn't feel too guilty about causing worldwide drownings. Sometimes two completely unrelated things are correlated just by random chance with no causal link at all. These correlations get called spurious correlations, and they can be hard to catch. But when the correlation is between two very specific things, like Nicolas Cage movies and all drownings in 3 feet of water when a dog was present, we should be suspicious that someone tried every weird subset of data until they found a relationship. Before we finish with correlation, I just want to warn you, R and R squared aren't everything. It's important to look at a scatter plot of data when you can. These are the Datasaurus dozen. These very different plots all have the same correlation, but we can see that the relationships are completely different. Correlation is an important piece of the puzzle when you're looking for a linear relationship between two variables. It goes above and beyond the y equals mx plus b and gives us information about how well that line explains the data. Understanding the relationships between variables and events helps us predict what things are going to happen in the future and also reflect on why things occurred in the past. A correlation can help you predict how much money you'll make after years of working your way up as a lemonade salesperson, or if watching that next Fast and Furious movie in the theater might encourage you to speed. According to an analysis by Harvard Medical School professor Anupam Jena, those two things could be related. Relationships are important, the humankind and the data kind. Correlation allows us to better understand relationships between data and maybe also the data of our relationships. Maybe you can find correlations between the amount of time you spend at work or school and how much affection your cat shows you. Mr. Fluffy misses you. Thanks for watching. I'll see you next time. Crash Course Statistics is filmed in the Chad and Stacy Imigholt studio in Indianapolis, Indiana, and it's made with the help of all these nice people. Our animation team is Thought Cafe. If you'd like to keep Crash Course free for everyone forever, you can support the series at Patreon.
All right, so now, yes, you can see you can make some silly decisions if you're not truly on top of what correlation really means. In fact, there was an interesting article I saw on the internet somewhere along the way where they listed a large number of correlations that sounded plausible, but you realize pretty quickly that they were pretty silly. Like there was a study done that showed that in the 80s, there was a strong correlation between professors' salaries and liquor sales. And so, you know, you might look at that and say, well, what does that mean? Do professors drink a lot? But what actually was happening was that these both happened in the 80s when the economy was extremely strong. So of course, when the economy is strong, you expect the sales of just about every product out there to increase, including liquor. And you also expect salaries to go up. So at the same time, just by coincidence, salaries for professors and liquor sales both went up. So in other words, the high correlation did not mean that one actually causes the other. So, you know, we have to be very careful when we analyze correlation figures, but just keep in mind, they do give us a sense of how closely the two variables move together, but we should not jump to the conclusion that one variable necessarily causes the other. That was the moral of that story. So anyway, let's get to the problem sets now. Actually, there's only the one for chapter 12. And it just basically covers everything we've done in this chapter 12. It's except, like I said, you'll not be asked to do the correlation or covariance measures because they're very, very complicated. So what we're going to do instead, as you can see, is look at the basic measures of association and the basic, measures of central tendency and measures of dispersion that we've learned in this chapter. Okay, so why don't we start here? Now, if you notice, I have conveniently for you highlighted the word sample. It's very important with these problems to pay very close attention to whether your data is a sample or a population. It will affect these two. If you get the wrong one, you will get the wrong answer for the variance and the standard deviation. Okay, so be careful. All right, so here I've highlighted it, but you know, let's face it, I might not do that on the test. If I forget, just remember, pay attention very closely to whether or not this is a sample or a population. All right, so the sample mean, as you remember, is X bar. And you'll just simply add up all your elements and divide by, in this case, 6, because there's 6 elements. Now, I just want to point out that for something like this, you do not have to sort them. We've been sorting a lot during this chapter, but for this application, that is not necessary. So you add them up and you get 9/6. And from that, we see that the sample mean is 1.5. And that's all you have to do. Now, the median, on the other hand, does require us to sort the data. So let's take care of that. That would give us -1, 0, 1, 2, 3, 4. Now we have an odd number of values. Sorry, an even number. If it was odd, it would be easier. With an even number of elements in our sample, we take the average of the 2 middle observations. Okay, in other words, you go to the middle and you say, oh, well, there isn't a single element in the center because we have an even number of values. The best we can do is take the 2 that are in the middle and average them out. Okay, so it's sort of like a compromise. And so what you're going to do is get 1 + 2 over 2 which is 3/2 or 1.5. Okay, if we had remember, if we had an odd number of values, you would have simply found the one in the center. But here with an even number, there isn't one in the center. Instead, you average out the two that are in the center. Okay. Now, as far as the mode is concerned, remember, this one also requires us to have sorted data. The mode is the most commonly occurring element in a sample. In this case, no element is repeated, so there is no mode in this case. Okay? That's the actual answer. There's no mode. There doesn't have to be one. There isn't a single value that's being repeated more than once, so therefore we simply don't have a mode at all. And remember, you can have one mode, you can have two modes, you can have three, as many as you want, but there also doesn't have to be a mode at all. And in this case, that's exactly what happened. All right, now the range. Now again, let me go grab the sorted data for you again so you can see what I'm doing. Oh, what happened? Somehow the 4 got left behind. All right, let me put that in here. So the range is simply the largest minus the smallest value. Which in this case is 4 minus a minus 1, which is the same thing as 4 plus 1, or 5. All right, so that's how you find a range. All right, so that's pretty straightforward. Now, the variance is a little tricky. Let me remind you what that formula looks like. So what that means is we have to go through all of the data and in each case subtract the sample mean of, which in this case was 1.5, if you recall. And then you'll square each of those differences, you'll add them up, and then when you're done, you'll divide by n minus 1. So let me go grab the numbers again so you can see them. All right, so here's what we're going to do. And by the way, again, in this case, we do not have to bother sorting the data. All right, so here's what we'll do. So I'm starting with x1 minus x bar squared. Then I go to x2 minus x bar squared. And then I'll have x3, x4. Oh, I'm going to run out of space, so let me write it like this. x5. And then finally x6. All of that is divided by 6 minus 1, because up here you notice it's the sample size minus 1. Now, this you can solve. You might want to think about solving it in 2 stages. Why don't you first calculate these, the values in the parentheses before you square them. You don't have to do it that way, but I find that it's easier to avoid mistakes that way. But that's up to you. So I'll show you how to do it this way. Because, you know, especially with all those negatives floating around, it's so easy to mess this up. But of course, you know that on a test, if you write out all the steps, I can give you partial credits if you make trivial errors along the way. Now we have to actually solve for these. Negative 2.5 squared, for example, is 6.25. Then we have 2.25, 6.25 again, another 2.25. Now, negative 0.5 squared is 0.25, as is positive 0.5. And now you're just adding them up and dividing by 5. So the numerator adds up to 17.5. When you divide that by 5, you get 3.5. And that's it, you're done. So yes, it looks like a catastrophe. It's kind of messy, but once you understand what you're doing, it's really not that bad. All right, now luckily, now remember, let's go back here. The standard deviation is last. Remember how easy that is. The standard deviation is simply the square root of the variance. The standard deviation is the square root of the variance for both samples and populations. So in this case, the sample standard deviation is the square root of 3.5, which is approximately 1.8708. All right, and that's all you have to do. So really, when you look at all these measures, honestly, the only one that's difficult is the variance. You know, the rest of them are pretty straightforward. All right. Now, what we're going to see next in problem 2 is that instead of a sample, this is now a population that we're looking at. So we need to make sure that we know that when we do these questions, because otherwise we're going to get the wrong answers. All right, now the mean, now also the notation is slightly different, although, you know, that's not such a big deal. Okay, let's see, the first one. So again, you're just adding them up. And in this case, dividing by 8. And so that turns out to be 12 over 8, or 1.5. All right, now for the median, we need the sorted data. And that's -2, 0, 1, 1, 2, 3, 3, and 4. Now, once again, there are an even number of values. We will find the average of the two values in the middle. Which ones are those? That would be the 1 and the 2. So just by coincidence, it's the same as we had in the first problem. All right. So that's all there is to it. And then the mode, again, remember, all we need is the most common value in that sample. And if you look at it carefully, you'll see something interesting. That, oh, what do you know? There's not only a pair of 1s, there's also a pair of 3s. Just the opposite of what we had before. So in this case, there are 2 modes, 1 and 3. And that's something you expect to run into once in a while. Okay, there can be 2, which is unusual. Most of the other measures, there's only 1 possible values. Excellent. Now, and you know, you might remember that with 2 modes, this population is said to be bimodal. All right, now you don't have to know that, but I just threw it in there because we did, I think, mention it during the chapter. But if you're interested in that, it just means you've got two most common values. Sometimes you see that with grades. You might discover, for example, that in a class you've got a lot of people who are getting B's and a lot of D's for some reason. You know, that would be considered bimodal. All right, now the range, I don't know what happened with this D here. The range, again, requires us to know or have this sorted data so that we can easily pick out the maximum and the minimum values. And the process is always the same. Equals the largest value minus the smallest value, which in this case is 4 minus 2, which is equal to 6. All right, so we've saved the best for last, the variance. Now remember, this time it's the population variance. And also remember, this one does not require sorted data. So what I'm going to do is go back here and copy these numbers. You can see what I'm doing. All right, now remember too, we've already determined that the mean is 1.5 from up here. All right, so that's been taken care of. So here's what I have to do now. First, let me rewrite for you the variance formula for a population. So now I have to go through them one at a time. And in each case, I'm subtracting the mean of 1.5. And then this time, you notice we're dividing by 8, the full size of the population, not n minus 1. This is the way in which the two are different. This is how the population variance differs from the sample variance. So now we can go through here and evaluate each of these squares. Okay, so if you analyze or evaluate the values inside the parentheses first, this is what you'll get. All right, and then you'll have 12.25, 2.25, another 2.25, 0.25, 6.25, 2.25 again, and then 0.25, and finally again 0.25, all divided by 8 is 26 over 8, or 3.25. And then, of course, the standard deviation is very simply the square root that would be about 1.803. Well, that's it. We're done. That scary document is done. So, well, I'll tell you what we should do, I think. So we're done with chapter 12. All the material is now finished. All the new material is completely finished. We've done all the chapter problem sets. And all that remains now is the sample final, which we can do on Monday. Let me just one more time show you what it looks like from Moodle. So you know what to expect. And you'll see it's a mixture of chapter 11 and 12, of course. And so we'll do this on Monday, and then there's combinatorics as well, of course. And then we'll be done with the course, sadly enough, except for the final exam. So then I can post the final exam. And like I said before, believe it or not, you can have all the way out until December 19th. So that's a long time. Try not to push it off that far because you'll start to forget what we did, unless you're really desperate for time. But just as long as we're in by midnight on the 19th, that's fine. If not, you might not get a grade. There's the problem. You want to be careful of that because if we miss the deadline, I don't know what happens, but it's not good. And so I will post the grades as I receive them. And so in other words, the sooner you send them in, the sooner I can do them. But, you know, again, it's up to you to decide when to finish it. But so what all this leads up to is that, and let me make an announcement about this. Yeah, here we go. I just want to add one more announcement. So next Monday, which is December 6th, I think. Does that sound right? Yes. We will go over the sample final. We will not meet on December 9th because we're done. Okay, so you're getting a day off because we finished early. You're getting a day off. The final exam is due on 12/19 at midnight. Between now and then, you can ask questions by email if you need to, or we can arrange a Zoom conference for office hours if you want them. Okay. In other words, I'm not disappearing. You know, you can send me email questions and say, oh, I don't remember how to do this. I don't understand this. And if that's not enough, you know, we can just have an actual Zoom conference and it would be like virtual office hours where I'm actually having a conversation with you in person or online rather than just answering emails. So that's all on the table. I just want to make sure that if there's anything you're not sure about, you can find out. And but I really think that the final won't be that difficult. And it'll be a good way to boost up your average because the final is worth more points than the first two exams. All right, so I guess in the meantime, I guess have a nice weekend and I'll see you all next Monday.
All right. Thank you. Take care.
See you later.
Bye.
Bye-bye. You're welcome, everyone. Yeah, I hope you had fun with this.